So this is section 2.5 in the textbook, an introduction to the periodic table. Periodic table lists the known elements. Its development started in the late 1800s. And if we order the elements in terms of their atomic number from left to right, top to bottom, we see regular repeating patterns of how atoms react, look, or form. For example, in group 1, lithium, sodium, and potassium are all shiny, soft metals that are very highly reactive. Or over here, neon, argon, and krypton. These are all gases that are totally unreactive. There are some characteristics of the periodic table that you should know. And in your notebook, you should write down the title. And then, using at least half a page, you can sketch an outline of what it looks like. And then we'll identify some places and some pieces on the table. First of all, you should know that the horizontal rows are called periods. Period 1 consists of two elements, hydrogen and helium. Period 2 then consists of lithium, sodium, skip across the blank area right here to boron, carbon, etc., all the way over to neon, so it has 8 elements in it. Period 3 then would start with sodium and end over here on the right hand side with argon. And there's period 4, 5, 6, 7, and in theory there will be more periods to the periodic table as well. The up and down portions are called groups or families. And the groups or families are numbered, and then some of them also has names. Many times now in modern periodic tables you'll see the groups or families numbered 1, 2, 3, all the way over here to 18. But on some periodic tables like this one over here, you'll see them separated as A and unnumbered, unlettered groups or families as well. And you see this called the 1A, 2A, and then this is the 3A, 4A, and then this is the 8A. And sometimes you'll see these numbered as the B groups as well. But it's all a matter of preference, and just the number 1 through 18 is usually the easy way to identify them. This group, way on the left-hand side, are called the Alkali Metals. The group right next to it are called the Alkali Earth Metals. This entire group from 3 through 12 right here, 3 through 12, that's kind of a bluish color right here. These are the transition metals. And these two elements right down here, lanthanide and actinide, actually are space holders because there should be another break in the periodic table right here for these elements that are down below. These are called the lanthanide and actinide series, or some people call them the rare earth elements, and they should fit in between groups 1 and 2 and then group 3 right here, down here. And if you ever see a real expanded periodic table that looks like this, where these families fit right in here, then you'll see this group right here, and then you'll see the remainder of the representative elements over here. That's the true expanded form. But they take this out and put it down here below to make it so it fits nicer on a piece of paper. Over here in this area, group 18 are called the noble gases. The noble gas family. You can see noble gases. And then group 17 right next to it are called the halogens. Group 16 is sometimes known as the oxygen group, and sometimes known as the chalogens or C halogens. 15 is the nitrogen group, 14 carbon group. And there are some areas of the periodic table that you can probably identify now that we went through them as well. There's a staircase that goes right here between boron and then it drops down here to silicon, and then it drops down here, and it continues on this direction like this. This staircase, this bolded, blacked in line right here, separates the metals. Everything over here is a metal except for hydrogen from the nonmetals. These are all nonmetals over here. The metals, left side of the periodic table, nonmetals, right side of the periodic table, except for a few bordering elements. The few bordering elements are called the semi-metals, and these are silicon, germanium, arsenic, antimony, and tellurium. They're ones that act somewhat like metals, somewhat like nonmetals. All the rest over here are metals. All the rest over here are nonmetals. Hydrogen is the one exception. On some periodic tables you'll see hydrogen listed over here as well, but it does belong over here just due to its number of electrons. You can use the periodic table to help you identify certain items or characteristics of many different elements. First of all, things in the same group or family act the same. I'm sorry, this one was beryllium. I don't know why I put sodium there. Lithium, beryllium, you can see it over here. These act like metals, and they all happen to have one outer shell or valence electron. You'll learn more what those are in a little bit later. This is group 2, and this group are all metals and have 2 valence or outer shell electrons. And then skipping across the transition metals right here, we get back to an area that with the group 1 and 2 make what are called the representative elements. The representative elements are only the groups 13 through 18 and the groups 1 and 2. And it includes hydrogen and helium as well, but it skips these middle metals right here. And these are the ones you can tell how they react a little bit more, and these are all metals anyway in here. They react fairly somewhat similarly to one another. In group 13 right here, it has 3 outer shell or valence electrons. Group 14 has 4 valence electrons, 15 has 5, 16 has 6, 17 has 7, and 18 has 8. And so the circled numbers right up here indicate the number of outer shell, aka valence electrons. And outer shell or valence electrons are super important because those are the ones that participate in bonding. Those are the ones that participate in making chemical reactions or formulas happen. So, on your periodic table, if you don't have them labeled already, please write the number of valence electrons, 1, 2, 3, 4, 5, 6, 7, 8. And we'll come back and we'll actually look at what kind of charges these cause when they gain or lose electrons in the next couple of sections. Section 2.6 in your textbook is called Molecules and Molecular Compounds. And if you check it out in your book, they give lots of nice colorful pictures of some molecular or molecules over here. And there are several elements that are found in nature in what are called their molecular form. 2 or more of the same type of atoms that are bound together. For example, the most common one is oxygen. Always exists as a pair, and it exists as O2. And you say it O2 like this. This is the way oxygen naturally exists. And there are 7 of these elements that you need to memorize that exist in a pair like this and exist as a molecular compound. The ones that exist like this have a special name. When they exist in pairs, they are said to be diatomic. Di is a prefix that means 2, and atomic means atom. So it means it's a 2-atom element. And the diatomic, there's an I right here, the diatomic elements are bromine, oxygen, nitrogen, hydrogen, chlorine, iodine, and fluorine. These all exist as pairs, O2, N2, H2, Cl2, I2, F2, when they're alone. One good way to remember these is on your periodic table. They form the shape of NOFClBrI. They form the shape of the number 7. And since there's 7 of them, 2, 4, 6, 7, you look at it and you say, oh, 1, 2, 3, 4, 5, 6. There's only 6 in here. And remember that hydrogen is also included in these diatomic elements. So some people call it the sneaky 7. And the reason they call it the sneaky 7 is because there's only 6 in the shape of a 7, but there's a sneaky one over here. So the sneaky 7 on the periodic table are the diatomic atoms or elements that exist. When 2 or more atoms come together and form a molecule, these are said to form a molecular formula. Some examples would be like H2O, where there's 2 atoms of hydrogen symbolized by this 2, and there's 1 atom of oxygen. Even though there's not a little number written down here, it's always assumed that there's 1 of them. For example, in carbon dioxide, there would be 1 carbon atom, and there would be 2 oxygen atoms, because this 2 tells you that there's 2 oxygens, and if there's no 1 written below the C, it's assumed that there's just 1 of them. The most simple ratio between atoms in a compound is given a special name. This simplest ratio is called the empirical formula. CO2 is an example of an empirical formula where the simplest ratio is 2 to 1. Water is the same thing, where there's a ratio of 2 to 1. There's an element called ethylene or ethene that's C2H4. There are 2 carbon atoms and there are 4 hydrogen atoms. This would not be an empirical formula though. This would be what's called a molecular formula. A molecular formula gives you the true or the actual total number of atoms in a compound. Now, if we wanted to find out what the empirical formula of ethene actually was, we could simply find the simplest ratio of carbons to hydrogens. And so the empirical formula of C2H4 would be for every 1 carbon, there are 2 hydrogens. And so CH2 would be the empirical formula for ethene, is that there's 1 carbon for every 2. This isn't the actual formula, it just tells you the simplest ratio of carbons to hydrogens. So the 2 terms you should come up with from there are empirical formula, simplest whole number ratio, and molecular formula, the actual true total number of atoms in a compound. There are a number of different ways to picture molecules, and many different ones are used in your textbook. One way to show a formula is by what's called a structural formula. And this shows that a hydrogen and an oxygen are connected to another hydrogen. This is a way of showing the structure of H2O. For example, in CH4, a good structural formula is to show the carbon connected to 4 hydrogens. How to draw these is actually the topic of Chapter 8, but many times before then you'll be given these structural formulas, and knowing that these mean the atoms are connected to one another with what's called a bond is probably a really important piece for you to be able to recognize. There are also spheres that are used, and sometimes ball and stick models are used as well. These shapes and formulas show up frequently throughout the book. You can see here's the structural formula. Here's what's called a perspective drawing formula, and you'll notice that a wedge in this formula indicates that the H is coming out of the page at you. The dashes indicate that the H is going back into the page in 3 dimensions, and the line right here indicates that it's in the plane of the page. So this is a way to depict the 3-dimensional structure of a formula. So ball and stick model, and then this is a space filling model right here. Well, once we know a little bit about formulas, we can now talk about when they gain or lose electrons. And these things that have gained or lost electrons have a fancy name in chemistry. Things that gain or lose electrons are called ions. I-O-N-S. Now there are positive ions, positive charge, and there are negative ions, ones with a negative charge. And since an electron itself has a negative charge, in mathematics we'd give it a charge of -1. If something gains a -1 electron, gains an electron, we say that it became negative because it's gaining a -1 thing, gaining an electron. So gain of an electron equals negative. Something becomes positive if it loses a negative thing, because minus and -1 in math class, of course, gives you a positive. And so a positive charge or a positive ion means that it lost an electron. These are positively charged things. Now there are fancy names given to each one of these. And there are regular repeating patterns on the periodic table for things that want to lose and gain electrons. Let's look deeper at things that form positive ions. First of all, a fancy name for positive ions. These are called cations. And a good way to remember a cation is to know that your cat is very positive, and because of that, it's very happy, and it's been eating a lot of food lately, so it's really chubby and it's got a lot of belly drag. But that's the cation, and the cation is positive, and the cation is something that has lost an electron. On the periodic table, things that like to form cations are things that can easily lose electrons. If you look at this little chart that's on page 60 in your book, positively charged ions are usually in group 1, and so above your periodic table you could put +1 for group 1. Positively charged ions are also usually group 2. The alkali earth metals form +2 ions almost always, and you can see +1 and +2 above mine. Over here on this side, the group 13 or 3A usually form +3 ions. They usually lose their 3 valence electrons, and you can see that on my periodic table right here. And then in group 4, it's kind of a toss-up whether it will lose or gain 4 electrons. And so sometimes you'll see it as +or -4, And then there are weird times where it's not either of those. So we won't identify that for sure. You can put a little question mark there as to whether that's going to act that way or that group will act that way or not. Let's look at negative ions. Negative ions are called anions. Anions are ones that gained an electron. And things that are anions are kind of like this ant right here, and they're actually kind of sad looking guys. They have negative little feelers, they have negative eyeballs, and they're not very happy. And so these guys are your antions right here. This is the cation, and this is the anion. I guess it doesn't really have a T in it, but you can remember that he's kind of sad and not very happy. Anions are things that gained an electrons, and the elements on the periodic table that generally like to gain electrons are group 15, group 5 right here. They usually like to gain 3 electrons, and they're usually -3. 16 likes to gain 2, they're -2. 17 likes to gain 1, and so they're -1. And you can see them on my periodic table right here. So on your periodic table now you should have several different things labeled. Let's just check to make sure that you have these things labeled on your periodic table. Here's my really rough sketch. This one should say 1 valence electron and +1. So over here maybe you want to label it valence electrons. And then here you can say what type of charge it normally has. And the charge is also sometimes known as its valence, or its ability to form a cation or anion. Group 2, usually +2. Over here, group 13, +3, and it has 3 valence electrons. 4, ± 4, 5, and then put -3 right here. I'm running out of room. I'm going to have to draw these guys over here more. 6, -2, 7, -1, and 8 right here is 0 for its charge normally. Check to make sure that you've got those numbers on your periodic table, and if you draw over the top of your ant, that's absolutely fine. These gaining and losing of electrons allows us to form formulas These formulas that are formed by the gain and the loss of electrons are called Ionic Compounds. We just talked about how these are ions and these are ions, and so then when you put 2 of them together, they're called an Ionic Compound. And Ionic Compounds form when you have a positive cation formed together in a bond or an attraction with a negative anion. Cations and anions form together to give you an ionic compound. Some examples of ionic compounds would be sodium, who usually forms a +1 cation, with an anion like bromine. Bromine is usually in this group, forms a -1 anion, and the positive and the negative ones would then end up transferring an electron, so both would have a neutral charge. Sometimes they don't form in perfect, really nice, neat numerical values. Like, for example, sometimes sodium will form with sulfur, and sulfur is in this group and is -2, and so you'd need 2 sulfur atoms, 1 each that is +1, to balance out the -2 electrons, and would accept 1 electron from each one. Sometimes you even see some that are like an uneven number for both. Like, for example, calcium, who's +2, right here, could form with phosphorus, who's -3. Well, that doesn't evenly go out, so you'd say I'd need 3 of these calcium +2s and 2 of these phosphorus, whoops, I'm sorry, I wrote this wrong, -3s right here. So then I'd have a total of +6ness right here and a total of negative 6ness to balance those out, so they'd end up with a neutral charge. This is a good overview and a good start. Sections 2.5 through 2.7 in your book. We'll pick up with naming and formula writing of different ionic compounds in the next video.